Have you ever wondered how your car's engine talks to its transmission? Or, how a simple click on your computer actually sends a command down a USB cable? Well, it all boils down to this fundamental language that wires speak. And today, we're going to decode how those abstract ones and zeros become real physical signals. This is the absolute backbone of our entire digital world.
So let's start with the big question. A computer thinks in ones and zeros, right? But what does a 1 actually look like on a wire? I mean, really look like? It's a question every single engineer has to answer. See, we've got to turn those abstract bits into something physical, something that can actually travel. And the simplest, most direct answer is a surprisingly powerful concept called NRZ Line Coding.
Okay, let's put this into perspective. Imagine you and a friend are in separate rooms, and you're trying to communicate with just a flashlight. The first thing you do is agree on a code, right? You'd say, hey, light on means yes, and light off means no. Well, it's the exact same challenge in electronics. We need a shared language, a set of rules to turn that binary information into electrical signals, and that's precisely where line codes come into play.
All right, let's get into the nitty-gritty. The name itself, non-return to zero, or NRZ, pretty much gives the whole game away. It tells you almost everything you need to know. With NRZ, when we send a bit, the signal goes to a specific voltage level, and it just stays there for the whole time that bit is being sent. It's a super direct, no-nonsense approach, which is what makes it so efficient.
To really get a handle on NRZ, let's step away from all the technical jargon for a second and think about something we all use every single day, a simple light switch.
So in the world of NRZ, sending a binary 1 is pretty much just like flipping that light switch to the on position. The signal jumps up to a high voltage, and just like that, the light in the room turns on. It's a really simple, direct, one-to-one representation of that bit. Easy, right? And what about a binary 0? Well, you guessed it. That's like flipping the switch off. In the most basic form of NRZ, this means the voltage drops all the way down to 0. So you have this crystal clear distinction. High voltage means 1, 0 voltage means 0. No ambiguity. Okay, now here's the most important part, and it's right there in the name. Non-return to 0. Let's say you need to send a long string of ones, like 111. The signal just stays at that high voltage level the entire time. The light switch, it stays on. It doesn't flick off and on again between each of those ones. That's the non-return part. Now, this light switch analogy actually has two main flavors, if you will. The difference between them all comes down to how we define that off state for a binary 0. And this brings us to the two big ideas, unipolar and bipolar NRZ. Okay, so unipolar NRZ is the most basic, straightforward way to do it. Just think of it like a one-way street. The signal is either at a positive voltage for a 1, or it's down at 0 volts for a 0. That's it. Bipolar NRZ, on the other hand, is more like a two-way street. It uses a positive voltage for a 1, but for 0, it uses an equal and opposite negative voltage. So the signal is always swinging between these two distinct poles, positive and negative.
This diagram right here perfectly shows the unipolar rule in action. Let's trace the data stream together. 1, 0, 1, 1, 0. You see the signal goes high for that first 1, then it drops flat to the 0 line for the 0. Then it pops back high for those two consecutive 1s, and finally returns to 0 for the last 0. See? Super clean, super simple.
All right, now let's look at the bipolar version using that exact same data stream. The 1s, they're still represented by that high positive voltage, but look closely at what happens for the 0s. Instead of just dropping to 0, now the signal swings all the way down to a negative voltage. It's a much more, dynamic way of representing the data.
Okay, so we've seen the two main types of NRZ. Let's put it all together now and see exactly how a data stream gets encoded using both of these rule sets. This is where it really clicks.
Let's walk through it. Our data stream is 10110. Applying the unipolar rule, we get a simple on-off pattern, right? The voltage goes high for a 1, then it goes to 0 for a 0. But with the bipolar rule, it's more of a push-pull pattern, high for a 1 and an opposite low or negative for a 0. The logic behind it is super simple, but as you can see, the actual electrical signals that come out look pretty different from each other.
So, NRZ's simplicity is its greatest strength, but it's also the source of its biggest weakness. There's a gotcha here, a hidden problem that can cause some major headaches in high-speed communication systems. So, what's the problem exactly?
Well, it all comes down to what happens when you send a long, unbroken string of the same bit over and over. If that signal just stays flat at a constant voltage for too long, the device on the other end can literally lose track of time.
You see, the receiver, the thing listening to the signal, it relies on those transitions between high and low voltage. We call these signal edges to keep its internal clock perfectly synchronized with the sender's clock. But what happens with a long string of ones or zeros in NRZ? There are no edges. It's just a flat line. And when that happens, the receiver's clock can start to drift, just a tiny bit at first, but soon it completely loses its place in the data stream. This is called losing synchronization. And for data transmission, it's catastrophic. It can turn perfectly good data into complete garbage.
All right, so what are the most important things you absolutely need to remember about NRZ? Let's do a quick recap of the key concepts we've gone over.
Okay, in a nutshell. First, NRZ is the simplest, most direct way to turn binary into voltage. Second, it comes in two main flavors, unipolar and bipolar, and the big difference is how they handle the 0 bit. And third, and this is the big one, its primary weakness is the risk of losing that clock sync when you have long, repetitive data streams.
So that leads to a really interesting question, right? If basic NRZ has this pretty fundamental flaw, how do real-world systems, like the ones in your car, actually get around it? Well, the answer lies in more advanced line codes, things like Manchester or 8B/10B encoding, which were invented specifically to solve this sync problem. But to understand any of those more complex codes, you have to have a rock-solid grasp of NRZ. It really is the foundation that everything else is built on.